Hello everyone, welcome to EOGENS 21. My name is Furkan Öztürk. I'm research assistant in University and I'm PhD student. Firstly, I want to say that I'm thankful for contributions to my PhD advisor, Tufan Çakır, and assistant professor Onur Aras. I will mention examination of dynamic displacements of a box culvert backfilled on one side. As you know, retaining structures can be constructed as full or relatively buried. Studies made by researchers have shown that such that structures can be significantly affected from earthquakes. This paper aims to investigate the dynamic response of the box culverts using well-known two approaches. In this context, firstly, I will define classification of culverts. Secondly, I will show seismic damage realized in culverts and wing walls. I will define purpose and investigate methods of the study. I will show mathematical model created. I will define seismic analysis procedure. I will mention finding. I will mention results and conclusions. Figure 1 shows culvert types used in Turkey. Firstly, box culverts. Secondly, arch culverts. Thirdly, bridge culverts. Figure 2 shows some damage under some earthquakes. This study investigates seismic behavior of the box culverts, considering backfill structure interaction. Interaction system has been formed by using quotes. In this context, approaches of Scott and Velasquez and Yunnan are used for mathematical model. In this study, while Model 1 defines mathematical model represented with Velasquez and Yunnan's approach, Model 2 defines mathematical model represented with Scott's approach. To investigate backfill structure interaction system has been considered for different soil conditions. Analyses in time domain have been carried out with Newmark method. The dynamic displacements of mathematical models are examined depending on changes in backfill stiffness, changes in frequency content, changes in mathematical model. Figure 3 shows dimensions of the culvert and backfill system. The soil structure system has been consisted of the culvert and backfill on one side of the structure. The backfill length has 10 H effective. In addition, length and width of the box culverts are 7.20 meter and 6 meter respectively. Height of the culvert is 7.4 meter from the bottom to top. Figure 4 shows mathematical model of the culverts and backfill. Within the framework of the mathematical model shown in Figure 4, dynamic responses are investigated by using two different models. In this context, while Model 1 Velasquez's approach defines, Model 2 Scott's approach defines. Figure 5 shows time histories of earthquake records considered in analysis. Figure 5a 1983 Coalinga earthquake. Figure 5b 2004 Backfilled earthquake. Figure 5c 1989 Loma Prieta earthquake. There are many approaches to classify using various parameters earthquakes. One of the most preferred methods is used in the study. According to this method, earthquake frequency content can be classified into three main categories depending on relation between peak ground acceleration and peak ground velocity. First of these is high frequency range, where is 1.2 less than the peak ground acceleration divided by peak ground velocity. The second is the intermediate frequency range, where is 0.8 less than or equal peak ground acceleration divided peak ground velocity less than or equal 1.2. The last one is considered as low frequency range, where is 0.8 bigger than peak ground acceleration divided by peak ground velocity. Table 3 shows range of earthquake records. Table 2 shows mechanical and physical properties of the backfilled soil systems. Table 3 shows the dynamic peak displacements obtained from box culverts. When Table 3 is examined in all earthquake records, it is seen that the peak displacements tend to increase in general depending on decreasing in soil stiffness. Figure 6 shows the dynamic displacements obtained from Model 1 and Model 2 for different earthquakes. The displacements can be seen that increase depending on decrease in soil stiffness when Figure 6a is examined. For example, while S1 backfill soil system produces 0.10083 meter peak response in Culvert, this response in S4 soil system occurs as 0.0187 meter displacement. There is about 125% difference between two dynamic peak displacement response. Similar trend is easily observed for park-filled loading in Figure 6b, where while top displacement of culvert for S1 backfill system is 0.0095 meter, the same response in S4 backfill system occurs at order of 0.0519 meter with an increase of 446%. Figure 7 shows time histories of dynamic displacements at top of the box culvert for Model 1. Figure 7 clearly shows that different earthquake contents can cause different response magnitudes on the box culverts. For example, while coiling earthquake in high frequency range results in dynamic displacement in order of 0.0187 meter for S4 soil system, Loma Prieta earthquake in low frequency range gives rise to displacement in order of 0.0382 meter with an increase 104.2%. It is possible to make some comparisons between the results produced by the models. Figure 8 presents an example for such a comparison. As expected, different results can be obtained with different assumptions. When Figure 8 is examined, it is seen that under the Coalinga earthquake, Model 1 produces 0.0160 meter displacement at 2.84 seconds for S4 ground system, while the same response for Model 2 occurs in order of 0.0187 at 3.50 seconds. As can be seen, the percent difference obtained between the two peak responses is around 16.88%. This study proposes a mathematical model using two well-known methods in the context of soil structure interaction. Also, earthquakes with 3 different frequency contents and 4 different backfill systems are used in the analysis. These results obtained are compared in terms of peak dynamic displacements depending on time history. Results show that the peak dynamic displacements change depending on soil stiffness. This change trends occurring in magnitudes of dynamic displacements generally indicates increase due to decrease in soil stiffness. In addition, comparisons made depending on frequency content shows that the magnitude of displacement can vary regardless of the frequency range. On the other hand, it has been observed that different mathematical models generally produce different responses. The results produced in this study are in order to show the general trend. It should Remember that more general judgments should be obtained by reproducing parametric studies. Thank you for your attention. For any questions, don't hesitate. Please contact with corresponding author Öztürk Furkan@gmail.com. Thank you so much.